Okay, so welcome to section 3.6, which is zeros of polynomial functions. Okay, so what is a zero? Let's recall. X equals to C, or I'll just make it easier. X such that f of x equals 0 implies x is a root. And a root is the same as a 0. So the remainder theorem, Okay, so the remainder upon division of f of x, a polynomial, by a linear divisor, x minus c is equivalent to f at c. So that is, i.e., f at c can be thought of as a remainder r of x. Okay, so for example, so evaluate or find the remainder for the following. Okay, so number one, let's say we have the polynomial 3x cubed minus x squared plus 4x minus 4 divided by, write that division symbol a bit better, divided by x plus 3. Okay, so here's our polynomial, and here's our divisor. And do you agree that x equals to negative 3 is the root? So because it's linear, we can use synthetic division. So let's put, negative 3 on the outside, our upside down division symbol, and our coefficients in descending order of our dividend, 3, minus 1, 4, and negative 4. So we'll drop down the 3 and start our process. 3 times negative 3 is negative 9. We're going to add this column together, which gives us a negative 10. Start again. Negative 3 times negative 10 is negative 30. I'm going to add these together, and what we get then is a negative 26. 3 times 2 would be 60 for 3 times 20. 3 times 6 is 18, so I claim that that's 78. Let's add these together, and I get a remainder of 74. And let's see if that's true. See if I did my math correctly. So what I'm saying here with the remainder theorem is that for my function, f of x being equal to 3x cubed minus x squared plus 4x minus 4. Yeah, that's the remainder. This implies that f evaluated at negative 3 is hopefully going to be 74. But let's see. So 3 times the quantity, negative 3 cubed, minus the quantity, negative 3 squared, plus 4 times the quantity, negative 3. minus 4. So what does this give us? 3 times, let's see, negative 27. And then minus, a negative squared is a positive, so this is minus a positive 9. 4 times a negative 3 is negative 12 minus 4. So 3 times 27, so this is negative 81. What did I do? I did something wrong, didn't I? Well, at least I found it now. So negative 81, and what do we have here? Minus 9, minus 12, minus 4. Drop down the 3, negative 9, negative 10, positive. Ah, that's where I went wrong. Right here, that's where I went wrong. That's a good thing I checked it. Okay, so we're going to go back and fix that. So minus 9 minus 12 is negative 21, so negative 25. Okay, so what I should get is negative 106. So I need to go back and fix my mistake, which was this sign right here. That sign should have been positive because 2 negatives make a positive, which means that this 26 is really a 34. Okay, good to check your work. Like I should have. Okay, so 3 times 3, that'd be 90 plus 12 is negative 102. And yes, oh thank goodness, it worked. It's a good thing I checked, so we'll check all of them just to make sure I know what I'm doing. Okay, so number 2. Where is that? Number 2. Okay, what's number 2? Let's try 5x to the 5th minus 4x to the 4th plus 3x cubed minus 2x squared plus x minus 1 divided by x minus 1. Okay. So here's our polynomial. And our divisor is x minus 1, which means our root is x equals to 1. So on the outside of my division symbol, my upside down division symbol, I have a 1. And then descending order on x, the coefficients are 5, negative 4, positive 3, negative 2, positive 1, and negative 1, respectively. Drop down the 5. 5 times 1 is 5. Add this. 5 minus 4 is going to be 1. 1 times 1 is 1. Add this column, we get 4. Now 4 times 1 is 4. Add this column, we get 4 minus 2 is 2. 2 times 1 is 2. Add this column, 2 plus 1 is 3. 3 times 1 is 3. Add this column, and our remainder should be 2. So hopefully, when I check my work, I will have done it correctly this time, but let's make sure. So I claim that the remainder is 2. So what is my function? My function, f of x, is 5x to the 5th minus 4x to the 4th plus 3x cubed minus 2x squared plus x minus 1. Oops. So this gives me that f at, what was my root? 1. So f at 1 is going to be 5 times 1 to the 5th minus 4 times 1 to the 4th plus 3 times 1 cubed minus 2 times 1 squared plus 1 minus 1. Okay, so this gives me 5 minus 4 plus 3 minus 2 plus 1 minus 1. So 5 minus 4 is 1. 3 minus 2 is 1. Plus 1 minus 1, so that's 3 minus 1 is 2, check mark. Okay, thank goodness, I can finally do math. Okay, so number 3. So let's say we have a polynomial 4x cubed plus 5x squared minus 2x plus 7, which we're going to divide by x plus 2. Okay. Oh, come on. So my root is negative 2. So I put a negative 2 on the outside. My upside down division symbol here. My coefficients are going to be 4, 5, negative 2, and 7. So I drop down the 4. So 4 times negative 2 is negative 8. 5 minus 8 is negative 3. 2 negatives make a positive 6. 6 minus 2 is 4. 4 times negative 2 is negative 8. So when I add these together, I claim my remainder will be negative 1. So let's make sure that that's true. I claim that this is my remainder. So what is my function? My function f of x is 4x cubed plus 5x squared minus 2x plus 7. So this means that f evaluated at negative 2 will be 4 times the quantity, negative 2 cubed, plus 5 times the quantity, negative 2 squared, minus 2 times the quantity, negative 2, plus 7. So this is 4 times negative 8, plus 5 times 4. 2 negatives make a positive 4 here, plus 7. So what do we have? 4 times 8 is 32. 5 times 4 is 20, and 4 plus 7 is 11. So 20 and 11 is 31, minus 32 is negative 1, check mark. It works. Okay, very good. Okay, so let's note. P of x can be thought of as q of x, the quotient, times the divisor, d of x, plus the remainder, r of x. So that implies that p of x is just the quotient, q of x, times the divisor, if r of x is equal to 0, right? So this would imply that q of x, or d of x rather, let's do d of x, is a factor of p of x, p of x. Okay, so definition. So if d of x is a factor of a polynomial function, f of x, little kitty snores, then we say that d of x divides, that's what we're defining, divides f of x, annotated by d of x, and then a straight up and down line, f of x, and that's read aloud. D of x divides f of x if d of x is a factor. Okay, so the factor theorem. How much room did I leave between one line? Okay, so the factor theorem so C, how about x equals to C, is a root of the polynomial f of x if and only if x minus C divides f of x. That is, x minus C is a factor. Okay, so for example, so use the factor theorem. The factor theorem to find all zeros slash roots, same difference, given one factor. So we want to find all. So let's say we have that f of x is equal to 2x cubed plus 9x squared minus 8x minus 15, given that 2x minus 3 divides f of x. That is, it's a factor. Okay, whoops. Well, if 2x minus 3 divides, let's do something. Remember, this is sneaky. It's got a coefficient. Let's factor out the 2. So this will be x minus 3 divided by 2, which means that x equals to positive 3 halves is the root. However, we have to be very careful because we have this extra 2 on the outside, so we have to remember that. So let's put 3 halves and our upside down division symbol. So in descending order, the coefficients of my polynomial are going to be 2, 9, negative 8, and negative 15. We're going to drop down the lead coefficient 2. And whenever we have a fraction, we divide by what's in the denominator, then multiply by what's in the numerator. Okay. So 2 divided by 2 is 1 times 3 is 3. So now we add this column. 9 plus 3 is 12, and we start again. 12 divided by 2 is 6. 6 times 3 is 18. Really? My goodness, these ants are crazy, biting my legs. Okay, so what do we have? 18 minus 8 is 10. So we start again. 10 divided by 2 is 5. 5 times 3 is 15, and yes, indeed, we have a remainder of 0, which is what we want. So the quotient here, q of x, is going to be 2x to the 1 power less than 3, so that's squared, plus 12x plus 10. But we're not done. This is actually not the quotient, because I have the extra 2. So remember, whenever we have that factored out, we have to divide by what we factored out. So the genuine quotient will be x squared plus 6x plus 5. So what does that mean? That means I can write my polynomial f of x as the factor that was given, 2x minus 3 times the quotient, which is x squared plus 6x plus 5. So now I just need to factor the quotient. So what two integers have a product of 5 and a sum of 6? And I claim that that's 5 and 1. So therefore the roots are going to be x equals to 3 halves, x equals to negative 5, and x equals to negative 1. So these are the 3 roots of that polynomial. Okay. So okay, so number 2. So let's say we have that f of x is equal to 3x cubed plus 2x squared minus 27x minus 18, and let's say we're given that 3x plus 2 divides f of x, meaning it's a factor. Okay, so once again, I'm going to focus on the fact that this has a 3. I'm going to factor out the 3, which means this is x plus 2 divided by 3, meaning that my root is x equals to negative 2 divided by 3. So let's put a negative 2 over 3, my upside down division symbol. Then I'm going to look at my coefficients in descending order of my polynomial, which are 3, 2, negative 27, and negative 18. So first step is to drop down the 3. Really? Now we divide by 3 because 3 is in the denominator now. So 3 divided by 3 is 1. 1 times negative 2 is negative 2. Add these together and thank goodness I get a nice lovely 0 because 0 times anything is 0. Add these together, we get negative 27. So now I'm going to take negative 27 and divide it by 3. That's going to give me negative 9 times 2 is positive 18. And as this should be, we were told it was a 0, so it is indeed a 0. So what is my quotient? Well, my quotient could be 3x to the 1 power less than 3, which is squared. No x's and minus 27, but that's not correct because I have this 3 here. So I need to remember to divide off that 3 that I factored out. So we get x squared minus 9 is actually the quotient. So f of x can be written as the factor that was given, 3x plus 2, times the quotient, x squared minus 9, which is a difference of squares. So we can factor that purple difference of squares as x plus 3 times x minus 3. And that comes from the difference of squares because a squared minus b squared factors as a plus b times a minus b. Why am I not able to write? Okay, so given that, we have that the roots are going to be x is negative 2/3. We already had that one. X is negative 3. And x is positive 3. So these are the roots. Okay, what number was that? Number 2. Let's do one more. Third time's a charm. So 1, 2, 3. Let's say we have my polynomial function is x cubed minus 3x squared minus 13x plus 15. 15, not 5. 15. So given that x minus 1 divides f of x. Okay, so thank goodness we have something we can deal with very easy over here. X equals to 1 is the root. Thank goodness I can just put a 1 on the outside, put my upside down division symbol. Steve Jobs. Okay, now I can take my polynomial and look at the coefficients in descending order, which is 1, negative 3, negative 13, and positive 15. We drop down the 1. We try to drop down the 1. 1 times 1 is 1. Put that in the next column and add. 1 minus 3 is negative 2. And we start again. Negative 2 times 1 is negative 2. We add this column together, we get negative 15. Oops, wrong color. Negative 15 times 1 is negative 15. Add this last column together and the remainder is 0 as it should be. So my quotient, q of x, will be 1 times x to the 1 power less than 3. So that's going to be x squared minus 2x minus 15. So I can factor f of x as the factor given, x minus 1, times the quotient, x squared minus 2x minus 15. So for the purple quotient there, I'm looking for two integers that have a product of negative 15, but sum to negative 2. Say negative 5 and positive 3 will do the job. So our roots are x equals to 1, x equals to 5, and x equals to negative 3. Those are the roots or x-intercepts. Okay, so now let's look at the rational roots theorem. So rational, meaning fractions, so rational roots theorem. Okay, so let's did I put that to the left far enough? I think I'm going to move that to the left just one bit. One more. Okay, so let's let f of x being equal to a sub n, x to the n, plus dot dot dot, plus a1, x to the first, plus a sub 0 be a polynomial. Such that the a sub i's are integers for all I. Then all real roots, not complex, but real roots, are of the form p over q, such that p divides a naught, or a sub 0, and q divides a sub n. So this is best shown by example. So for example, use the rational roots theorem to find all real roots. So use the rational roots theorem to find all roots of the following. Okay, so number 1, let's say we have x cubed minus 3x squared minus 25x plus 75 is equal to 0. Okay, so this can be written as 1 x cubed minus 3x squared minus 25x plus 75 is equals to 0. So that means that a sub 3, which is my a sub n in this case, is 1. And a sub 0, which will be what q goes into, is 75. So I know that p divides a sub 0. So p divides 75. So that means that p is going to be plus or minus 1 always. Now 75 ends in 5, so I know it's divisible by 5. Is it divisible by 15? Well, let's see, is it divisible by 3? I should have done that. Well, 7 plus 5 is 12, so it is divisible by 3, so plus or minus 3, which means it's also divisible by 3 times 5, or 15. And we know for a fact it's divisible by 25. And it's divisible by itself, so plus or minus 75. I need to move this over. I don't have a lot of room. Yeah, let me draw that a bit better. Okay, so that's all possible divisors of 75. But Q, I'll just use this What color should I use for Q? So Q divides 1. So that means that Q is just plus or minus 1. So I do need to move this a bit. So this implies Q is just plus or minus 1. Okay, so the set of all P divided by Q's possible rational roots, so P divided by Q, is just going to be the same as P. And the reason that is because plus or minus 1 divided by plus or minus 1, it's still going to be plus or minus. It'll just change the negative to plus and the plus to minus, but it's still the same thing. So this is going to be 1, 3, 5, 15, 25, and I forgot the 75, didn't I? Unbelievable. Plus or minus 75. Okay. I erased it and then completely forgot it. Let's move this over to allow for that one more. Plus or minus 75, all divided by Q, which is just 1. Plus or minus 1. So it's basically the same set as P, because anything divided by 1 is a whole number. So let's look if 1 is a possible root. So let's clean this up. So P over Q will be plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15, plus or minus 25, and plus or minus 75. You don't want to start with the high numbers. Let's start with 1. So if I plug in 1 minus 3 is negative 2, minus 25 is negative 27, plus 75 is not a root. So let's go ahead and give 3 a shot. See if that'll work. So try. X equals to 3. So I'm going to put x equals to 3 on the outside of my division symbol. And then I'm going to have my coefficients in descending order on my polynomial to see if it goes in. 1, negative 3, so 1, negative 3, negative 25, and positive 75. Okay, so let's see if 3 goes in. Drop down the 1. 1 times 3 is 3. Add these together, we get 0. That's always nice because 0 times anything is 0. Add these together, we get negative 25. Times 3 is going to be negative 75. Look at that. It is indeed a root. Thank goodness. So that means I can factor my polynomial as, so x cubed minus 3x squared minus 25 minus 25x plus 75 can be factored as x minus 3 times the quotient, which is x to the second power, minus 25. Well, that's the difference of squares. So this is x minus 3 times x plus 5 times x minus 5. Okay, so my roots, all of my rational roots, I think I'm going to try and give myself more room here. Don't know if I have it. Okay, I don't really have it. That's unfortunate. Okay, so my roots are going to be 3, negative 5, and positive 5. And these are rational because their whole numbers are always over 1, so they can technically be termed rational roots. Okay, so number 2, let's do x to the 4th minus 2x cubed minus 7x squared plus 8x plus 12 is equal to 0. Okay, so let's rewrite this as 1 x to the 4th minus 2x cubed minus 7x squared plus 8x plus, what color did I use for? I used purple. Plus 12 is equals to 0. Okay, so I'm going to say q divides 1. So this means that q is just plus or minus 1. And p divides 12. So that means that p is going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, and plus or minus 12. Okay, so therefore the set P over Q we know that division by plus or minus 1 is just going to change the signs. So all the plus or minuses become minus or plus, which is equivalent. Okay, so all of our possible P's over Q's are going to be 1, 2, 3, 6, 12 divided by 1. So that is all of my possible roots are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, and plus or minus 12. Okay, so I guess we can start with 1. So let's look at 1. 1 minus 2 would be negative 3. Minus 7 is negative 10. Plus 8 is negative 2. Plus 12 is not 0. Okay, so now let's try maybe 2. Let's guess 2. So I'm going to put a 2 on the outside. Hopefully that'll work. We have to test them all until we get ones that work. Okay, so what is my polynomial? Coefficients are 1, negative 2, negative 7, positive 8, and positive 12. So let's try 2. So drop down to 1. 1 times 2 is 2. Add this column together, we get 0, my favorite number. Because 0 times anything is just 0. Add this column together, we get negative 7 times 2 is going to be negative 14. Add this column together, we get negative 6 times 2 is negative 12. So yes, thank goodness. So the remainder here is 0, which means I can rewrite my function. Or do you know what? I'm going to show you something that works. So if we look now at this last guy, it's not 12, it's now 6, plus or minus 6. So I can try again with the 1s, the 2s, the 3s, and the 6s. So let's see. 1 minus 7 is negative 6. Minus 6 does not work. However, this would be 1 cubed. So that would be negative 1 plus 7. So I believe negative 1 works. So I'm going to try negative 1 on the outside here. And I'm going to do another upside down division symbol with the remaining guys we have here. So drop down. So 1 times negative 1 is negative 1. Add these two together. 0 minus 1 is negative 1 times negative 1 is positive 1. Add these two together. Negative 7 plus 1 is negative 6. Negative 6 times negative 1 is 6. Add these two together and we do indeed get 0, so that does work. Once again, my last number is still 6, so I still have the possibility of all of these being roots. So we could try again. Let's see if 1 is a root. So 1 minus 1, no, 1 is not a root. 4 minus 2, no, that's not going to work either. How about 4 plus 2? Let's try a negative 2 on the outside. See if that works. So negative 2. So I'm just getting these numbers from inside that P over Q box, right? I'm just trying all these numbers on the outside until we get ones that work. And by ones that work, I mean that the remainder is 0. So drop down the 1. 1 times a negative 2 is negative 2. Add this column, we get negative 3 times negative 2 is positive 6. Add this column and we get 0. Okay, very good. So that's going to be x minus 3, so I'm going to try 3 as my root. Keep on going. You can translate these into quotients, each of them. I'm just showing you an easy way where all of these guys all came from. Here. Okay, so drop down the 1. 1 times 3 is 3. Add these two together and we get 0. Okay, so the quotient is just 1, which it should be because 1 times anything is itself. So I claim that f of x can be written as x minus the first factor, x minus the second factor, x minus the third factor, and x minus the fourth factor, provided this is a polynomial of degree 4, which it was. So let's write what it is. Nope, wrong. I claim that f of x was this long polynomial here. Copy. I'll get rid of that equals 0. And I'll make that 12. Blue. Okay, so I claim that this can be factored now as x minus the first guy, 2, times x minus a negative 1, so that's plus 1, times x minus a negative 2, so that's plus 2, times x minus 3, and there we are. So the roots will be x equals 2, 2 in the first case, negative 1 in the second case, negative 2 in the third case, and 3 in the fourth case, namely just these guys here. Those are our rational roots. Remember, all whole numbers are over 1. So let's do another one. So number 3. Let's say we have 2x cubed plus x squared minus 7x minus 6 is equal to 0. Oh boy, okay, so let's rewrite this as 2, thank goodness, a different number than 1. X cubed plus x squared minus 7x minus 6 is equal to 0. So I know that q divides 2, so that means that q is going to be plus or minus 1 or plus or minus 2. I know that p divides negative 6, so that means that p is either plus or minus 1, plus or minus 2, plus or minus 3, or plus or minus 6. So now we finally have a p over q that's going to be more interesting. So the set of all possible p's over q's is now going to be plus or minus 2, plus or minus, plus or minus, plus or minus, plus or minus. Okay, so all p's, which are 1, 2, 3, 6, then 1, 2, 3, 6. Now why did I list p twice? Well, because the q's are now plus or minus 1 or plus or minus 2. Okay, so what are all possible p's over q's? Okay, 1 over 1 is 1, 2 over 1 is 2, 3 over 1 is 3, 6 over 1 is 6. Then plus or minus 1/2. 2 over 2 is 1, I already have that, plus or minus 3/2. 6 over 2 is 3, I already have that. So this is all possible roots, p over q. Okay, I always like to start with 1 just to see if that works. So that would be 2 plus 1 is 3, minus 7 is negative 4, so that does not work. What about negative 1? That'd be negative 2, that'd be negative 1 plus 6. Oh, negative 1 actually works, so I'm going to put negative 1 as my first root on the outside because I did it and it seems to work. So I'm going to put my coefficients in descending order, so that would be 2, 1, negative 7, negative 6, 2, 1, negative 7, negative 6. So we drop down the 2. Two times a negative 1 is negative 2. Then we add this column together. So 1 minus 2 is negative 1. Times a negative 1 is a positive 1. Add these together, we get negative 6. Times a negative 1 is a positive 6. And when I add those together, I do get a remainder of 0, which is good. Okay. So I know that it'd be squared, so 2 minus 1 minus 6. That's 1 doesn't work. What about 2? Let's try 2. So I'm going to go to the next root that isn't 1. Let's try 2. So we have 2 on the outside. Let's do this. And actually, let me move that 2 up. Okay, so we drop down, lead 2. So 2 times 2 is going to be 4. Add this column together. 4 minus 1 is 3. 3 times 2 is going to be 6. Add this column together, and we do indeed get 0. Okay, so what remains would be 2x to the first. So 2x plus 3. Well, I already know that that's going to be negative 3/2. So that's going to be this guy here. So let's show that that's true. Let's do negative 3/2 on the outside. So that means, actually, let me give myself more room here. First step is to drop down the 2. And remember, we divide first. So divide by 2 is 1 times negative 3 is negative 3. Then we add these together and we get 0, which is good. However, I've got a 2 left over, not a 1. Well, in order to get that 3/2, I would have had to factor out the 2. So I divide by 2. This is one of those sneaky ones. So my remainder should be 1. Or, actually, I can show you this way. So f of x equals 2. We had, let me go ahead and just copy this. Copy. Paste and change it to blue. So I claim that we can write this as x minus the first factor, x minus the second factor, x minus the third factor, times the final factor of 2. So this will be x, minus a negative 1, so minus a negative is plus. Then it'll be x minus the second factor, 2. Then it'll be x minus a negative 3/2. But the 2 is still left from this last quotient. Now notice if I were to distribute that inside, that 3/2 would go away, but this is sufficient. Okay, so we're still on the first page out of 3. This is a long section. Okay. Okay, so let's recall. Oops, I forgot to list the roots, sorry. So x equals 2. Now what color should I use? What color did I use here? I used purple. Okay, so x equals to -1, 2, and -3 halves are the list of fruits. Okay, so now we can recall. So recall. If I have x squared plus a squared, we can factor this over the complex numbers as x plus a times I, x minus a times I, where I is equal to the square root of -1. So what this means is that x is equal to plus or minus ai. And these are complex numbers, right? So note. So for all complex numbers, z equals to a plus 0i, elements of the complex numbers, implies that z is also real, because the imaginary part, b is equal to 0. So that is, for all real numbers x, this implies x is also an element of the complex numbers, whose imaginary part is 0. Okay, so this gets us to the fundamental theorem of algebra. So fundamental theorem of algebra. Okay, so let's let f of x be a polynomial of degree n larger than 0, which basically means it's linear or larger. So then f of x has n linear factors over the complex numbers over C. That is, i.e., it est, f of x can be written as x minus c1 times the quantity x minus c2 ... times the quantity x minus c to the n, such that the c sub i's are complex integers for all subscripts i's. So for example, so find all complex solutions, real and imaginaries. So real numbers are still complex numbers, but the converse is not true. So find all complex solutions, real and imaginary, for the following. So number 1, let's say we have x cubed minus 8x squared plus 25x minus 26 is equal to 0. Okay, so this does not factor by parts or by grouping. So what I'm going to do is I'm going to look at all possible p's over all possible q's. I always start with 1. Here's my p's, here's my q's. So I'm going to start with the set of p over q's. P over Q. I know it'll start as plus or minus 1 over 1. Okay, does 1 work? 1 minus 8 is negative 7. Plus 25 is going to be 18 minus 26. No. What about negative 1? Minus 1 minus 8 is negative 9 minus 25. No, that doesn't work. So let's try plus or minus 2. Okay, if I try 2, I wonder if that'll work. So I'm going to just go ahead and try it right away. So 2 into... I always can do 1 by sight. 1 is always the easiest one. No pun intended. Okay, so let's do our coefficients. Will be 1, negative 8, 25, and negative 26. So we drop down the lead coefficient 1. 1 times 2 is 2. We add this column. Negative 8 plus 2 is negative 6. Negative 6 times 2 is negative 12. Add this column. So 25 minus 12 is 13. Times 2 is 26. Add the column, we get 0, which is what we wanted. Okay, so now what two integers multiply to 13 and add to negative 6? Well, that's going to be pretty miserable, isn't it? Well, let's look at this. So I know right now I can write my x cubed minus 8x squared plus 25x minus 26. I can write it as x minus 2 times the quotient x to the second power minus 6x plus 13. Okay, well, let's look at this. Let's use the quadratic formula. Namely, x is equal to negative b plus or minus the square root of b squared minus 4ac. 4 times 10 is 40, and 4 times 3 is 12, so that's 52. All over 2a. Okay, hopefully everyone knows the quadratic formula. So what does this give us? This gives us 6 over 2 is 3, plus or minus. Okay, the difference between 52 and 36. So that's 46 would be 10, plus another 6. So that's going to be the square root of negative 16. So I claim that this is 3 plus or minus 4i. So the roots are complex, right? So the set of all possible roots are going to be 2, then 3 plus 4i, that's my complex, one of my complex roots, and 3 minus 4i is another complex root. So those are the roots. Okay, so let's do another one. Number 2. So let's say we have 3x cubed minus 4x squared plus 11x plus 10 is equal to 0. Okay, so how did I start it here? Yeah, let's look at all of our q's and all of our p's. Okay, so the set of all possible p's over q's will be, so I always start with my, oh, come on, easy numbers. So let's try. First one, 1 over 1, because 1 goes into 3. Okay, so 3 minus 4 is negative 1 plus 11. Oh my goodness, it works. 1 works, so let's start with that one. Gotta love it when 1 works, because 1 is nice. So, upside down division symbol, coefficients in descending order are going to be 3, negative 4, positive 11, and positive 10. So we drop down the 3. 3 times 1 is 3. Add these together, we get negative 1. Negative 1 times, oh no, it doesn't work. I lied to myself. Okay, that's not a negative 10, that's a positive 10. Oh well, does not work. Okay, so at least we know that. Let's try -1 instead of +1. Would that work? Well, that would give us -3, and this would sum to -7. Nope, that's not going to work either. Okay, well, we tried. Let's try 2 instead. My next guy is going to be ±2. So let's try that one. I knew it couldn't be that easy. Okay, so 2 times 3 will be 6. Add these together. 6 minus 4 is going to be 2. 2 times 2 is going to be 4. Right? Add these together. We get 15. Nope, that's not going to work. What about -2? Okay, if we use -2, what are we going to get? Okay, so if we use -2, we get -6, which is going to give us -10. Then -10 times -2 is going to give us +20. Nope, that's still not going to work. Okay, oh my goodness. So I guess we have to move on to 3's. Okay, 2, 5. Let's try 5, because a factor of 10 is 5, right? So all factors of 10 will be ±1, ±2, ±5, and ±10. So I've done 1, 2, and 5. The factors of Q are ±1 and ±3. I'm not dividing by 3 just yet. I want to see if we can get an integer in here. Let's see if 5 will work. Let's try 5. So we drop down the 3. 5 times 3 is 15. Minus 4 is going to be 11. So 11 times 5 is 55. I can see that's not going to work. Okay. Let's try -5 then instead. This builds character, doesn't it? Okay, so 5 times 3, -15. So 4 and 15 is 19. 19 times -5 is going to be -95. I can tell right away that's not going to work. Okay, so it looks like we have no choice but to use fractions. Okay, so the next set of fractions will be 1/3. I wonder if 10 would work. No, I don't. No, so let's use ±1/3. Will that work? So if I have 1/3 out here, what happens? 3 divided by 3 is 1. -4 plus 1 is 3. Divided by 3 is 1. So add 11 plus 1 and we get 12. Divided by 3 is not going to leave us with 0. Okay, so let's try -1/3 instead. Okay, so what do we have here? Oh, this is going to give me ugly fractions, so I don't think that's going to work, but let's see. So this would be -1, and this would be -5. So that's going to be 5/3. And I can assure you right now that that's not going to work. So let's go on to the next one, which is 2/3. So ±2/3. Okay, so let's put a 2/3 out here. Okay, so 3 divided by 3 is 1 times 2 is 2. So this is going to be -2. Divided by 3 times 2 is going to be a fraction. I don't think that's going to work. Let's do negative instead of positive. See if that works. Okay, so 3 divided by 3 is 1 times a negative 2 is negative 2. Add these together, we get negative 6. Now negative 6 divided by 3 is negative 2 times negative 2 is positive 4. Add these together, we get 15. 15 divided by 3 is negative, we're going to have 5 times a negative 2. Holy free holy, we actually got it. Negative 10, oh my goodness. Okay, so that means my remainder is 0. Those were miserable numbers, weren't they? Okay, so I had to go all the way out there. So my quotient has a factor of 3. I'm going to factor out that 3. So what remains if I factor out the 3? So my Q, at this point, my quotient is going to be 3x squared minus 6x plus 15. I can factor out the 3, and it'll be x squared minus 2x plus 5. So what two integers multiply to 5 and add to negative 2? Well, that's going to be a problem, isn't it? So I claim so far that my function, which is here, 3x cubed minus 4x squared plus 11x plus 10 can be written as x minus a negative 2/3 times 3 times the quantity x squared minus 2x plus 5. Okay, so let's look at this quadratic. I claim that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So once again, this is going to be 1 plus or minus root 16, a negative 16, so this is 4i. So all of my x's are going to be negative 2/3, 1 plus 4i, and 1 minus 4i. Okay, I think that's enough of that for now, isn't it? Oh, wait, no, that was only 2. I have to do 3. So let's make this one a bit easier, shall we? Okay, let's say we have x cubed plus x squared plus x plus 1 is equal to 0. So this one we can actually look at as we would a normal polynomial, in that I can factor by grouping. I notice that each grouping of 2, if I factor out an x squared from the first 2, there's an x plus 1 remaining. If I factor a 1 from the second grouping, there's an x plus 1 remaining, meaning I can factor the x plus 1, and what remains will be the x squared plus 1. Okay, so factoring x squared plus 1, that's a complex, so I know that that'll be x plus 1i times x minus 1i. So now my roots are going to be, in the first case, negative 1, in the second case, negative I, and in the third case, positive I. That one was nice, because I didn't use synthetic division. Okay, enough of that. So let's note. So complex roots always come in conjugate pairs. So complex roots come in conjugate pairs. Conjugate pairs. That is, i.e., it est, if x minus z divides p of x, this implies that x minus z bar also divides p of x. And let's see if that's true. Well, these are complex conjugate roots, I and negative I. These are complex conjugate roots, 1 plus 4i and 1 minus 4i. These are complex conjugate roots. 3 plus 4i and 3 minus 4i. So if you have one complex root, you always automatically have 2. Okay, so definition. So, or let's recall before I do a definition. So let's recall. X squared plus a squared factors over c. Factors over the complex number c, not r. So, because n equals to 2 is the power on x, this implies 2 complex roots by the fundamental theorem of algebra. Okay, so definition. Okay, so x squared plus a squared is called an irreducible quadratic. So that's what we're defining, an irreducible quadratic over the real numbers r. So meaning it cannot be factored over the real numbers. So let's note all irreducible quadratics, factor over z. Sorry, not over z, over c. Meaning everything can be factored over the complex numbers. Okay, so the next is going to be Descartes' rules of sign. Actually, do you know what? I think that's, yeah. Okay, I'll leave it. So let's go to the next page. Descartes' rules of sign. Or rule of signs. Not sure where the S goes. Okay, so let's let f of x be equal to a sub n, x to the n, plus dot dot dot, plus a1x plus a naught, or a sub 0. B, actually that's a terrible sub 0, isn't it? Sub 0, be a polynomial function, or just a polynomial. Then we have the following. Number 1, the number of positive real roots, so the number of positive real roots is either, not iter, well, either equal to the number of changes in sign, or is less by that, or is less than that by a multiple of 2. Multiple of 2. So number 2, make this a bit darker. Number 2, the number of negative real roots. The number of negative real roots is either equal to the number of changes in sign of f at negative x, or is less than that, by a multiple of 2. Okay, holy free holy. Let's do this, shall we? So for example, use Descartes' rules of sign. So use Descartes' rules of sign. Now this is SIGN sign. To find the number, or the possible number, of real positive and real negative roots. Meaning we don't want I. Okay, so number 1, let's say we have that f of x is equal to x cubed minus 2x squared minus 5x plus 6. Okay, so how many changes in sign? Let's first write it out. F of x is x cubed minus 2x squared minus 5x plus 6. So there's 2 changes. So that means either 2 or 0 positive real roots. Zeros. So it's either the number of changes in sign or less than that by a multiple of 2. So now let's look at f of negative x. So let's do f of negative x is going to be negative x cubed then minus 2x squared, then plus, so I want to do a different color, plus 5x and plus 6. So there's only one, oh, oops, wrong color, shoot. This is green. Okay, so there's only one change in sign. So that means that there is one negative root. So one change in sign, because I can't have negative one real negative roots. So that means that there is exactly one negative real root. Okay, well, let's see if that's true. So is there a way that we could factor this? Should we try? What are all possible real roots? Well, we have 6 over 1. So does 1 work? 1 minus? Yeah, 1 does work. So I'm going to try the root of 1 into this polynomial, which has coefficients of 1, -2, -5, and 6. Hopefully one will work. 1 times 1 is 1. Negative 2 plus 1 is negative 1. So negative 1 times 1 is negative 1. Minus 5 is negative 6 times 1 is negative 6. So yes, a remainder of 0. It is a factor. Okay. So let's try again. 1 minus 1 minus 6 is not 0, so let's try 2. So, and is 2 a factor of 6? It is. So that's good. Okay, so drop down the 1. 1 times 2 is 2. 2 minus 1 is 1. 1 times 2. Nope, that's not going to work. Okay. So let's try negative 2, shall we? So this will be negative 2, so that's negative 3. Negative 3 times negative 2 is positive 6, so that does work. So we get 0. So that's just x minus 3, so I claim that 3 is a root. So I'm just going to put 3 on the outside here, because x minus 3 is 0. So we drop down the 1. 1 times 3 is 3. Add these together, my remainder is 0. And that works, okay. So I claim that my roots are 1, negative 2, and 3. So what's interesting about this is as follows. So I claim that my roots are going to be 1 and 3, and then negative 2. So do you agree that there was 2 real roots and 1 negative root? Sorry, 2 positive roots and 1 negative root, which is nice. So I can actually plot this, can't I? I know my x-intercepts, and I know it's S-shaped overall, right? And each of them is linear, so let's note. Let's put these down here. Okay, so my x-intercepts are at negative 2, positive 1, and 3. Do I have a y-intercept of 6? Oh boy. Okay, maybe I should take this down then. So my y-intercept is when x is 0, and that's at 6. Okay, so we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Okay, so my zeros or my intercepts are at 1, 3, negative 2. Those are my x-intercepts, and my y-intercept is at 6 when x is 0. And I know that this is overall S-shaped, so I know the end behavior is going to be going down here somewhere and then eventually going up here somewhere. But all of these are linear factors, so I know that each of them is going to be little lines. So this is going to come up, go through here, then come back down. Well, that's terrible. It's actually going to probably come up above it. Let's see if I can draw something that looks a bit better. Something like that. Okay, and then it's going to go down. And these are also going to be little lines here. And I'm going to have a nice smooth curve like this. And there we are. Okay, so that's S-shaped, and it has all the necessary intercepts and roots. Note that everything was real. There were no complex roots here. So okay, let's try another one. Okay, so number 2, do I have enough room? No, I think, well, I'll start here. So number 2. So we have that f of x is equal to x to the 4th. So that's parabolic, plus 2x cubed minus 12x squared plus 14x minus 5. Okay, so I claim for the positive real roots, it's going to be x to the 4th plus 2x cubed minus 12x squared plus 14x minus 5. So that's 3 changes in sign. So that means that there is either 3 or 1 positive real root. Because there's 3 changes or 3 minus a multiple of 2. Okay, now let's look at f at negative x. So to the 4th is still positive. To the 3rd will be negative. Okay, squared will still be what it is. So negative 12x squared is going to change the sign on the 14, so it'll be negative 14x and minus 5. So there is actually no changes in sign for this. Oh, yes, there is, from the first term to the second. So yeah, because this is positive here. So there's 1 change in sign, so this is 1 change. So there's only 1 negative real root. So the better way to write this, there exists x in R minus a root. There exists 1 x in R minus, I should say. Exists 1. Can't even draw a straight line. Okay, so up here I should write it, there exists so here there exists 1 or 3 x in R plus roots. So 1 or 3. Okay, so let's see what they are, shall we? So let's try 1. If I look at 1, 1 plus 2 is 3, minus 12 is minus 9, plus 14 is 5, minus 5. I think 1 works, so let's try 1. Let's put 1 on the outside. Upside down division symbol. Okay, so what do we have? Coefficients in descending order will be 1, 2, negative 12, 14, and negative 5. Drop down the 1. 1 times 1 is 1. Add this column together. So we get 3. 3 times 1 is 3. Minus 12 is negative 9 times 1 is negative 9. Add this column together, we get 5. Times 1 is 5. Add this column together, we get 0, which is what we want. Okay, so let's try 1. That's 4. Yeah, okay, let's try 1 again. So it looks like 1 might have a multiplicity of 2. Drop down the 1. 1 times 1 is 1. plus 3 is 4 times 1 is 4. Minus 9 is negative 5. Oh, wow, I keep on doing the wrong color here. It should all be blue. Okay, blue. So let's see, negative 5 times 1 is going to be negative 5. So my remainder is 0. So what do integers multiply to negative 5 and add to 4? That looks like it's going to be complex, doesn't it? So I claim so far that my function f of x factors as x minus 1 squared, and my quotient is x to the 2 less, so x squared, plus 4x minus 5. Okay, so that means that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Actually, these are real. Okay. So this is going to be negative 2 plus or minus. Oh, did I do something stupid up here? I think I did. Yeah, 4 over 2. This should be 2i. 2. Sorry about that. 2. Okay. 2. 2. Did I do it up here too? Yes, I did. 2. My goodness, what is wrong with me? 2, 2. Yeah, these 60-hour work weeks for 9 hours of pay just are not working out anymore. So 36, the square root of 36 over 6 over 2 is 3i. No, just 3. So we get 2 roots, namely 1 and negative 5. Nope, that's not going to work. Negative b plus or minus square root. Yeah, it will work actually. Okay, never mind. So that means that x is going to be positive 1 is a root of multiplicity 2. Then I had 1 again, so actually it's a root of multiplicity 3. Oh my goodness, okay. And 5. Sorry, negative 5. So let's see if that works. How many? I had 3 changes in sign. So I had 3 positive real roots, and all 3 of them were 1. Why? This is because the multiplicity of 1 was 3. There were 3 of them, right? 1, 2, 3. Okay, and how many? There's only 1 change in sign, so I knew there was at least 1 negative root, and that is negative 5. Okay, so if I have a multiplicity of 1 is equal to 3, and a multiplicity at negative 5 equal to 1. What is the overall shape here? The overall shape is parabolic, going uphill. So let's see what this would look like. And I think we'll stop with this one. So x and y coordinate axes. My y-intercept is negative 5. Okay. So 1, 2, 3, 4, 5. X and y. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so what were my intercepts? They were negative 5 for x and 1 of a multiplicity 3, because I had 3 of them, right? So let me reiterate what that means. Let's put this off to the side here. How do I want to do this? Okay, so what this means is I can factor this as, oh, come on, Steve Jobs, x squared, x minus 1, and x plus 5, because remember those are the roots, so I have to do the opposite. So this is really x minus 1 cubed and x plus 5. So that's where we're getting the multiplicities from. Okay, I know that my y-intercept was at -5. So 1, 2, 3, 4, -5. And I know that this is overall parabolic, right? So the end behavior is going to be up in this direction. Oh, okay. Like so. And up in this direction, like so. Okay, but what do I know about the behavior? Near -5, it's linear, right? So the multiplicity is 1, so it's just a little line. However, the behavior near 1 was S-shaped. So it's going to be a little S-shaped graph there. I can bring this down right there. Then I can just connect the dots. This is going to be, oh boy, this is going to be a terrible graph. I'm going to try it, probably just something like so. And then it comes up like so. Something like that. Okay, so there is an estimate to my graph of f of x. Okay, and we've been at this for a long time, so I think I will let you guys go at this point.